a wonderful day to everyone watching this video. So for our group, we will be discussing the lesson that which is the wave properties of light. So, to give a brief introduction to this topic, for centuries, people believed that light simply behaved as a particle, largely due to Isaac Newton's hypothesis. But following that, we have Thomas Young that which disproved this theory by using his double slit experiment to prove that light does not simply behave as a particle but also as a wave. Now, with that out of the way, I would like to call on Serna to discuss the objectives of this lesson.
Number 1. Discuss the wave nature of electrons and light. Number 2. Spell out correctly the complete names of some scientists who conduct experiments showing that light behaves like waves. Number 3. Demonstrate appreciation of wave nature of light through daily experience of the various light phenomena.
What is light? In the late 16th, Newton explained many of properties of light by assuming it was made of particles. Because of Newton's prestige, his support of the particle theory of light tended to suppress their point of view. Newton did not specifically say that light had to be of particles. He did describe many of properties of light in terms of particles, including refraction and reflection. He did not see evidence for wave properties such as interference. And as in this quote, diffraction, this led him to favor particle. Newton's reputation kept the physics community from seriously considering light as wave for about 100 years. It seems that very little research was done during that time to actually resolve the issue. With that in mind, allow me to call Alacri to introduce Thomas Young and his contribution.
Young's contribution. Young first experimented with the pinhole and sunlight and saw interference fringe. In 1816, Fresnel wrote a paper looking at night in terms of waves and predicting such effects as reflection and interference. He was disappointed to hear that Young had already reported these effects. In 1818, the French academics' annual competition consumed diffraction and interference effect and hoped to obtain convincing evidence for a corpuscular theory. In response to the challenge, Fresnel showed that the shadow behind a small sphere would have a bright spot at its center. Young's original double slit experiment was done with double pinholes. The sketch of the production of the interference pattern was done by Young. Thomas Young got a new realization and said to himself, "This is a good time to get out the ripple tank if you have not already done so." It's also like a demonstrate interference with microwaves and sounds. Includes Thomas Young's portion. Now, allow me to call on Domingo to discuss other significant people.
Other significant individuals. In 1900, Lord Rayleigh and James Jeans realized, based on their understanding of Maxwell's equations, that light energy in a black body should be distributed equally among all the wavelengths that will fit inside the black body. This assumption leads them to propose that most of the light should be short wavelengths, thus the ultraviolet catastrophe. To solve the problem, Planck made the unprecedented and ad hoc move of making the energy of a wave related to its frequency and not its amplitude as in classical theory. He also stated that light was released in bundles of energy that Gilbert Lewis in 1926 called a photon. Planck never liked the idea. He said, "My futile attempts to fit the elementary quantum of action somehow into the classical theory continued for a number of years, and they cost me a great deal of effort." Moving into Hertz's discovery, it goes as follows. Hertz discovered the photoelectric effect in 1887. It was shown that the energy of the electrons emitted did not depend on the brightness of the light, but the frequency. Taking a cue from Planck, Einstein used his idea of a light quantum to explain the effect and was later awarded the Nobel Prize for his work. Einstein and Planck seemed to bring us back to a particle nature for light. Another example that might be considered at this time is Compton scattering. Now, allow me to call on Glasang to continue the discussion.
Prince Louis de Bargy proposed the idea that particles can also be thought of as waves of his PhD thesis. It was a difficult sale and required the intervention of Einstein. By 1920, it was shown that the crystal produced the diffraction patterns and is struck by X-ray in 1923. The Barger's ideas were verified by experiment like that of Davison and Germer, who bombarded crystals with the electrons and got a similar patterns. It has been shown that the experiments similar to Taylor's can be done with electrons, giving the same result. So, what is light, particles, or waves? Heisenberg's idea let us think about the particles as a sum of waves. The more you know about the particle's properties, because it is a sum of waves, the less you know about its waveness, and the vice versa. It is something instructive to have a student add waves using a graphing calculator or computer graphing program. More quantum strangeness comes when we consider a harmonic oscillator. If you think about a spring in a classical sense, it can have a zero spring potential energy when it stops vibrating. Erwin Schrödinger, in an attempt to explain the waves associated with the electron, developed his wave equation. Given the mass of the particle and the force to which it is subjected, the spring for the harmonic oscillator, Schrödinger waves, and in turn to the possible energy or the zero-point energy, and that the system can't go below that energy. Moving on to the next subtopic, we have Aman Laras to enlighten us.
Now, let us move on to another aspect of this topic. How does light respond when directed to a material, or how does a material respond when struck by a light? You see, visible light, also known as white light, consists of collection of components colors. These colors are often observed when light passes through a triangular prism. Upon passage through the prism, the white light is separated into its components like color red, orange, yellow, green, blue, indigo, and violet. The very common phenomenon to all people of separating white light into its different color is the rainbow. Everyone enjoys watching a rainbow glimmering against a dark stormy sky. This effect is called dispersion. Dispersion is the separation of visible light into its different colors. Each color of light has a distinct wave frequency, and different frequencies will bend in varying amount as the light ray passes through a medium like prism or raindrop. Those with higher frequency have shorter wavelength, and light spectra with lower frequency have longer wavelengths. Colors of visible light spectra that have shorter wavelength like blue, indigo, and violet will be deviated more from their original path than the colors with longer wavelength like red, orange, and yellow. That is the reason why red is on the top while violet is at the bottom of a spectrum. The emergence of different colors of light from a triangular prism at different angles lead an observer to see the component colors of visible light separated from each other, the rainbow phenomenon.
Let us now move on to scattering. Scattering light is a phenomenon in which light rays redirect from the straight path when striking an obstacle like dust or gas, molecules, water, vapor, etc. Scattering of light gives rise to many spectacular phenomena such as Tyndall effect and the red hues of sunrise and sunset. The following are several samples of light scattering, starting with the first one. Why is the sky blue? Why is the red sunrise and sunset? Why do clouds appear white? The colors we see in the sky are due to scattering of light. Additionally, there are three main types of solar radiation scattering, which are Rayleigh scattering, May scattering, and lastly, non-selective scattering. I am now calling on Alakri once again to explain the first of the three types of scattering.
Rayleigh scattering. It is named after Lord John Rayleigh, who first described it in 1870s. Rayleigh scattering occurs when the scattering particles are small compared to the wavelength of light interacting with it. These particles are mostly molecules of atmospheric gases. The amount of scattering is inversely proportional to the wavelength, meaning lights of shorter wavelengths are scattered more than lights of longer wavelengths. Rayleigh scattering accounts for the blue skies and red-orange sunrise and sunset. When light enters the atmosphere, violet and blue lights are scattered the most. However, our eyes are more than sensitive to blue than violet lights. Thus the sky appears blue. At sunrise or sunset, sunlight travels farther through the atmosphere. The longer distance would mean much of the blue wavelengths or shorter wavelengths are scattered completely, thus leaving only the longer wavelengths, yellow, orange, and red. This explains why we have an orange-red sunrise scattering. The sky would appear black at daytime.
May scattering. May scattering occurs when the wavelength of the electromagnetic radiation has a similar size to the atmospheric particles. May scatter generally influence radiation from the near UV through the mid-infrared parts of the spectrum. The scattering of the light mostly occurs in the lower portion of the atmosphere where larger particles are more abundant and dominant. When cloud conditions are overcast, pollen, dust, and smog are major cause of May scatter. It produces general haze in the atmosphere. With this in mind, let's move on to the last type, solar radiation scattering, non-selective scattering, to be explained by Manlaras.
Non-selective scattering. So this type of scattering happens when the particles are much larger than the wavelength of light. Non-selective scattering scatters all radiation evenly throughout the visible and thermal portion of the spectrum, hence the term non-selective. Common particles responsible for non-selective scattering are water droplets and large dust particles. For example, when it comes to clouds, all wavelengths are scattered almost equally cause the fog in clouds to appear white. So with the three main types of solar radiation scattering done, let us now move on to interference.
Interference is the combination of waves moving into intersecting or coincident paths. Maybe you have seen the spectrum of colors reflect from a soap bubble, from an oil slick or gasoline on a wet road, from the glossy surface of a compact disc. silvery scales of some fishes, abalone shells, and cappies. These are all produced by the interference of light. That concludes the explanation of interference. Now I call on Marba to discuss the next topic, which is diffraction.
Now, to discuss diffraction, it is the bending of light around an obstacle and subsequent spreading of light waves into the region behind an obstacle. Examples of these obstacles are a slit, a wire, a hole, strands of hair, feathers, strings, or a straight edge, and the like. When the obstacles are illuminated by a beam of monochromatic light from a point source, fuzzy shadows are casted at the edges. The shadows are bordered by alternating light and dark bands upon close scrutiny. The amount of diffraction depends on the width of the slit compared to the light's wavelength. Very little diffraction occurs when the slit is considerably larger than the wavelength. A substantial diffraction is observed when the width of the slit is comparable to the wavelength of the light. The perfect analogy for this is the spreading of water waves through an opening. The smaller the opening and the greater the wavelength, the more the water spreads out. Now, with that out of the way, I would like to officially close this report by calling on Litigio to do so.
To summarize, this lesson explained the wave nature of light and electron through important experiments and everyday observation. Early scientists like Isaac Newton supported the particle theory of light, but later experiments by Thomas Young and Augustine Jean Fresnel demonstrated interference and diffraction, proving that light behaves as a wave. Further discoveries by Max Planck and Albert Einstein show that light also has particle properties like protons, leading to the idea of wave-particle dualities. Louis de Broglie later proposed that electrons can behave like waves, which was confirmed by electron diffraction experiment. The lesson also discussed key wave properties of light. First, the dispersion, separation of white light into colors like rainbow. Second, the scattering, explains blue skies and red sunset. Third, the interference, overlapping of waves causing bright and dark pattern. And last, the diffraction, bending of light around obstacles. Overall, the lesson shows that both light and electrons exhibit wave behavior, helping us understand many natural phenomena we see every day. With that, I officially conclude our report. Thank you everyone. See you next time.